Hello everyone, welcome back to Mining of Massive Datasets. In this lecture, we're going to cover a very important topic, clustering. We're going to kick off our discussion of clustering by looking at some applications of clustering that will tell you why we need clustering in the first place. Then we're going to look at the overview of the most common methods used for clustering. The basic problem of clustering is quite simple. We have a cloud of data points. Here you see data points in 2 dimensions. And we'd like to get some understanding of the structure of the data points beyond just seeing them in the 2 dimensions. For example, it's intuitively clear by looking at these points that there are 3 groups of points here. There's a group of points that group together here. There's another group here. And there's a third group here. And it looks like we have 2 outliers that don't fall into any of the groups. The goal of clustering is to find groups like this, except in much higher dimensional spaces than 2 dimensions. More formally, given a set of points and a notion of distance between points, we want to group the points together into a number of clusters or groups. And we want to group them together so that members of a cluster are close or similar to each other using the notion of distance that we've defined previously, and members of different clusters are far away from each other or dissimilar from each other. Usually, the points that we'll be dealing with will live in a high dimensional space, a space with thousands or hundreds of dimensions. And similarity will be defined using a distance measure from among the distance measures that we have covered earlier, such as Euclidean, cosine, Jacquard, or edit distance. Going back to our example, here we have points in a 2-dimensional space. And let's say our distance measure is Euclidean. Observe that points in the group that are highlighted are close to each other by Euclidean distance and are closer to each other than they are to points outside this group. We'll call this group a cluster. Similarly, we have 2 more clusters based on the similar notion. And finally, we have these 2 outliers that are not close to any of the clusters. Now, that example looked easy, but in general, clustering is a hard problem. For example, here we have a group of points, and you can see that the different colors actually denote different clusters. But the problem you notice is that unlike the previous example, where the clusters were cleanly separated from each other, in this case, the clusters actually overlap with each other. For example, there are some blue points that are among the orange points here and some among the green points here. And you can notice that the clusters are kind of smeared over and mix into each other, and it's hard to find clear boundaries between the clusters as in the previous example. So these are the kinds of real problems that we'll have to tackle when we deal with clustering in the real world. So why is clustering hard? Clustering 2 dimensions actually looks quite easy. Clustering small amounts of data also looks easy. And in most cases, looks are actually not deceiving. Clustering in 2 dimensions or small amounts of data is actually very, very easy. The trouble starts when you increase the number of dimensions. Many applications don't involve 2, but tens or hundreds or thousands or even tens of thousands of dimensions. And high dimensional spaces are fundamentally different from low dimensional spaces. The problem is that in high dimensional spaces, almost all pairs of points are at approximately the same distance from each other. And so it's not intuitively clear how to group them together. These problems will become apparent as we work with high dimensional spaces. Let's look at some real applications, starting with SkyCat. SkyCat is a catalog of 2 billion astronomical objects, and each object is represented by its radiation signature in 7 dimensions or frequency bands. The problem is to take these 7-dimensional data points and cluster them into real-world objects, such as galaxies, stars, quasars, and so on, which are more similar to each other than they are to other things. As a second example, let's look at clustering CDs. Now, intuitively, music divides into categories, and customers prefer a few categories or genres of music. But what are categories really? Right? We'd like to represent a CD by a set of customers who bought it. And we'd like to say that similar CDs have similar sets of customers. And CDs naturally group or cluster together based on the customers they have. For example, there might be a group of CDs that are that are classical music, and they have a group of customers who are classical music aficionados, and there's another group of CDs that are punk rock that are bought by a different set of people. Another example is clustering documents. We'd like to group together documents on the same topic. But what's a topic really? A topic is just a set of words that appear together frequently. Now, documents with similar sets of words might be about the same topic, right? So we want to cluster documents based on their similarity in the space of words. A dual problem is to find topics instead of documents. A topic is just a group of words that co-occur in many documents. So we could instead look at words in the space of documents and cluster those rather than clustering documents in the space of words. And when we do that, we'll find topics instead of document clusters. Let's talk briefly about distance measures. We've looked at various distance measures such as cosine, Jaccard, and Euclidean. And depending on the way we represent the objects that we're clustering, one or the other of these distance measures may be more appropriate. For example, let's look at our examples of documents or music. And different ways of representing documents lead to different distance measures. We might represent a document as a set of words or a bag of words that appear in the document. In this case, the appropriate distance measure to use is the Jaccard distance, since we are dealing with sets. Alternatively, we can think of a document as a point in the space of words. Here there is one dimension for each word, and each document is an n-dimensional point. A dimension I is 1 if word I appears in the document and 0 otherwise. Since we've represented documents by points, the natural distance measure here is Euclidean distance between the points in space. Alternatively, we can think of a document as a vector in the space of words. A document is a vector from the origin to the vector x1 through xn, where xi is 1 if word I appears in the document and 0 otherwise. And when you think about documents as vectors, the natural distance measure is the angle between the vectors, or the cosine distance. Notice that each different way of representing the same object leads naturally to a different distance measure. And depending on the application, a certain representation and distance measure might make more sense than another. Now that we understand distance measures, here's an overview of the important methods of clustering. The two important methods of clustering are hierarchical methods and point assignment methods. And within hierarchical methods, we can either go bottom-up or top-down. Bottom-up methods, or agglomerative methods, start with each point in a cluster by itself. Now, once we have each point in a cluster by itself, we repeatedly combine the two nearest clusters into a single cluster. And we stop at some point and we have a set of clusters. Divisive or top-down methods initially place all the points in the same cluster and then keep recursively splitting the clusters until we end up with the desired number of clusters. Point assignment methods work differently. In point assignment methods, we always maintain a set of clusters, let's say k clusters at any point in time, and then we repeatedly assign a point to its nearest cluster. And we proceed until each point is assigned to some cluster.